This is our solar system, consisting of most of the major planets without their moons. You can guess that the working of these planets are very complex. Today we are going to see the Kepler's law of planetary motion, which explains the working of these heavenly bodies. Hello, I am Dr. Upendra Maurya. I am starting a video lecture series for intermediate students for understanding the concepts of physics. You are watching Easy Physics. Let's get started. In this video, we are going to see how Kepler decoded these natural patterns of heavenly bodies and made beautiful laws explaining the motion of these planets. Before we dive into the Kepler's law of planetary motion, let's see what was the understanding way before the Kepler. Since inception, human believed that the Earth is the center of the universe and all the planets, stars, including Sun, revolves around the Earth. This model was called geocentric model. In the start of the 16th century, Nicolaus Copernicus observed some anomalies and proposed heliocentric model. As per the Copernicus, Sun is at the center and all planets including Earth revolves around the Sun in circular orbit. So the heliocentric model of Copernicus says that Sun is at the center, all planets revolve around the Sun in circular orbit, and third, since the orbit is circular, the speed of rotation is same throughout the orbit. So here comes our hero of this video. Kepler's all three laws actually modified or improved the heliocentric model proposed by Copernicus. Kepler was employed by Danish astronomer Tycho Brahe. Kepler assisted Tycho Brahe for a year and so before Tycho Brahe died. Now Kepler inherited lifelong work of Tycho Brahe consisting of accurate astronomical observations. Kepler, just like his mentor Tycho Brahe, struggled to fit the circular orbit for the Mars. It was giving very inaccurate result. Then Kepler employed the elliptical orbit for the Mars and it gave fairly accurate result. With time, Kepler realized that elliptical orbit gives fairly accurate result and was suited for giving accurate prediction for planet position in solar system. With time, Kepler realized that all the planets moving around the Sun in elliptical orbit. So the first law of Kepler states that all the planets move in elliptical orbit with the Sun situated at one of the foci of this ellipse. Let us try to understand the Kepler's first law. You can see the motion of the Earth along the Sun in circular orbit. Once this orbit transforms into ellipse, the Sun cannot be at the center, it has to shift to one of the foci point. So the path of the planet is elliptical. Now if the orbit is elliptical, the distance of the planet is going to change at every point from the Sun. Then what happens to the speed of the planet? Is it going to be constant or it is going to change? Kepler observed that the speed varies throughout the orbit. At nearest point, the speed is highest, while at the farthest point, the speed is lowest. From this, the Kepler deduced the second law, which is called the law of area. Once you understand the law of area, you will understand what kind of mathematical genius Kepler was. The law states that a line that connects the planet to the Sun sweeps equal area in equal interval of time. This was the plain observation made by the Kepler. Kepler was not aware of the underlying mechanism or concept behind this because he was not aware of the Newtonian mechanics such as angular momentum, laws of motion, inertia, etc. because Newton was not born by then. Now let's try to understand the Kepler's second law. We can see as the Earth is very close to the Sun, the speed of the Earth is higher. If it is very far away from the Sun, the speed is less. So as per the Kepler, as we have already seen, dA upon dt is going to be constant. That means if it is very far, then it is traveling very slow, and if it is very close to the Sun, then it is traveling relatively faster. That means it is covering the equal area in equal interval of time. So in 3 days, at every point in this orbit, in this elliptical orbit, the Earth is sweeping equal area. Now let us try to understand the basic science behind this and underneath mechanisms for this law. Now let us try to find out the area swept by Earth in 3 days. So this, if you consider the nearly circular orbit, so this becomes r, that is a radius. Now the curve swept is, this will become r times theta if this angle is theta. So now we can write that area dA, small area, should be equal to, this is nearly triangular, so 1 by 2 base r times height is r times theta. So that will give us the value 1 by 2 r square theta. So this is the small area. If we take in any particular time period, small duration of the time, this becomes dA upon dt is equal to 1 by 2 r square d theta by d time. We know that the rate of angular change is called velocity, angular velocity. So we can write the formula dA upon dt is equal to 1 by 2 r square omega. We all know the concepts of momentum. So momentum is equal to, suppose P is the momentum, is equal to mass into velocity. So angular momentum, suppose we represent in terms of, in the form of L, so that will be equal to r times m times v, r times the linear momentum. We all know that the v is equal to r omega, linear velocity is r times the angular velocity. If we substitute it here, we will get L is equal to r times m times r omega, which can be further simplified as m r square omega. That means L divided by m is equal to r omega, which we can substitute it here, and we will be getting dA upon dt is equal to L divided by 2m. Now students, this is very important formula. In this formula, dA upon dt as observed by the Kepler is going to be constant, and mass is also, mass of the planet is also constant everywhere. That means this law is only possible because of law of conservation of angular momentum. Let me write this formula again. So this is dA upon dt is equal to L divided by 2m. That means at every point in the orbit, the angular momentum remains constant. That means L is equal to mrv. This product should be constant at everywhere. So what does that mean? Suppose Earth is at this point, so angular momentum at this point will be mr times v1. Suppose this is first point. After some time, suppose the Earth is at this point. At this point, if L2 is the angular momentum and mrv2. Okay, so this is the second point. As per the law of conservation of angular momentum, this L1 should be equal to L2. That means mr1 v1, that should be equal to mr2 v2. Since mass is going to be constant, that means we can remove this mass. That means r1 v1 should be equal to r2 v2. That means if any particular point, if radius is decreasing, the velocity should increase, and any point if radius is increasing, the velocity should decrease. So if I play the animation, we all can see as the planet is coming closer, because of law of conservation of momentum, angular momentum, its velocity has to increase, and when it is very far away from the sun, its velocity will reduce. Similarly, as we can see, at the longer distance from the sun, its velocity is less because radius is more. At closer to the sun, its distance is from the sun is less, then the velocity will increase. This is the law of conservation of angular momentum. I hope you understood the Kepler's second law. Kepler published the first two laws in the year 1609, and it took nearly 10 years for the Kepler to publish the third law. Kepler always wondered, is there any relation between the orbital time period and distance of the planet from the sun? Kepler tabulated all the data and gave a thought. So in this table, the planets are in the column 1. Second, this is the distance, their semi-major axis in 10 raised to 10 meters. This is orbital time in years. So you can see for the third planet, this is our third planet, the Earth. The distance is 15 into 10 raised to 10, and it takes nearly 1 year to complete its orbit. For the planets above the Earth, their distance from the sun is relatively lesser, as well as their orbital time period. For the planets which are below the Earth, they are having relatively longer distance from the sun, and their orbital period is also higher compared to Earth. Kepler checked the ratio of t square divided by a cube for all the planets, and he surprisingly got the value nearly similar. Kepler realized this amazing correlation, and he proposed his third law that states t square is directly proportional to a cube. That means the square of period of every planet is directly proportional to cube root of its semi-major axis. Now we understood how Kepler figured out the third law. Now let's try to understand what actually third law states. So as per the Kepler's third law, t square is directly proportional to a cube. That means the planet which is very close to the sun will have the shorter orbital period. So we can see the planets like Mercury is having a shorter period compared to the Mars. Earth take nearly 1 year to complete the orbit, and subsequently Jupiter is having higher, and if we consider Pluto, that will be the highest one. I hope you understood these three laws of the Kepler. I hope you enjoyed the session as well. Thanks for watching. See you in the next video.